Welcome back to another explainer. Today, we're climbing one floor higher in our structural design journey. Over the last few sessions, we've explored the raw physics of pre-stressing concrete. How to squeeze it, calculate the stresses, and track force losses over time. But today, we're shifting gears from the physics to the philosophy. We are talking about limit state design criteria. We're tackling one massive, fundamental question today by looking at the engineering philosophies behind massive, critical structures, like the Mumbai-Ahmedabad bullet train. And that question is, how do we decide exactly how much pre-stress is enough? Think about it. If we put in too little, the bridge fails. But if we put in too much, we're wasting millions of dollars in materials. To really understand the modern answer to this question, we first need to understand why the old methods failed so spectacularly. So here's our roadmap for today's explainer. We'll cover the bridge building dilemma, two extreme design flaws, the limit state solution, running the numbers, and we'll wrap up with the intelligent distribution of safety. All right, let's jump right into part one, the bridge building dilemma. Picture this. You've just been tasked with designing a massive pre-stressed bridge girder. You have a huge responsibility on your shoulders. Now, historically, engineers approached this monumental task from two completely opposite ends of the spectrum. For decades, they essentially argued between two extremes. On one side, you had the elastic or working stress method. The whole philosophy here is to be ultra safe. You keep stresses so incredibly low that the concrete never exceeds 40% of its strength. You design it so it'll never crack, never deflect, and practically last forever. But on the flip side, we have the ultimate load method. These are the collapse thinkers. They'd say, forget daily service life. I'm going to design this beam to just barely survive the absolute maximum load it'll ever see right before it collapses. They save a ton of material, but they completely ignore what happens to the bridge day to day. Which brings us to part two extreme design flaws. Well, living at the absolute extremes rarely works out in the real world, right? The sheer inefficiency of the elastic method makes it totally inadequate for pre-stressing. Why? Because it completely ignores the section's ductile reserve strength. Meaning, it doesn't realize that an overloaded pre-stressed beam won't just suddenly snap. It actually has a reserve phase where it acts just like standard reinforced concrete. Furthermore, it illogically treats certain dead loads, like the bridge's own weight, exactly the same as highly uncertain live loads, like a sudden crowd of people. Plus, it completely ignores long-term losses from things like creep and shrinkage over 30 years. To put that into perspective, if we use this ultra-conservative method for India's incredible new Chenab Bridge, the highest railway bridge in the world, the beam would be so tremendously thick that it would literally collapse under its own weight. So yeah, it's safe on paper, but practically uneconomical. On the other hand, if we rely on the ultimate load method alone, we run into a different kind of nightmare. Sure, the bridge won't collapse under a massive overload, but it allows your bridge to develop wide cracks under normal, everyday service loads. Water seeps into those cracks, the steel rusts, and boom, the bridge fails prematurely from corrosion, not from a lack of raw strength. It also completely ignores deflection. A beam designed this way might sway and deflect 100 millimeters under a standard bus. That is absolutely terrifying to the public, not to mention it damages the road surface. And critically, it gives you absolutely no guidance on how much initial pre-stressing force you actually need to prevent the beam from cracking during construction. So what's the fix? That is part three, the limit state solution. We obviously needed a middle ground here, which led to the global standard and the correct solution for modern engineering, the limit state method. Think of it as the Goldilocks approach. In simple terms, a limit state is just a condition beyond which the structure ceases to perform its intended function. We essentially establish performance boundary lines, looking at that historical dilemma and saying, hey, why not just design for both daily comfort and ultimate survival? The modern approach, specifically laid out in the Indian standard IS 1343-2012, demands a mandatory two-tier check for every single pre-stressed member. Step one happens at transfer, the initial stage, where we use elastic analysis because the concrete is young and we absolutely must prevent it from cracking. Step two happens at service, the final stage, where we check the ultimate strength to ensure it can survive a worst-case scenario overload. So we're really getting the best of both worlds here. We're essentially splitting our engineering worries into two distinct categories that both have to be passed. First up is the ultimate limit state, or ULS. This is your pure safety check. It answers the big question: will the concrete crush or the steel snap under the heaviest possible load? Second, we have the serviceability limit state, or SLS. This is your comfort and durability check. It ensures the train vibrations won't annoy the passengers, the beam won't noticeably deflect, and the concrete won't develop those nasty microcracks under normal use.
Okay, let's see how this actually plays out in part 4, running the numbers.
Let's cement this concept by running the actual math on a simple pre-stressed beam. Say we have a 200mm wide by 400mm deep beam made of M50 grade concrete with an effective pre-stress of 800 kilonewtons. Before we dive into the results, it's really cool how the limit state method uses different targeted safety factors rather than just one blanket multiplier. We use a 1.0 load factor for everyday service loads because, well, we know exactly what those normal loads are. But we use a 1.5 partial safety factor for the ultimate limit state, artificially amplifying the dead and live loads to test the structure against the heaviest possible unpredictable ultimate loads.
Watch this method work its magic when we look at a 120 kilonewton meter service load. First, the elastic method checks the top fiber stress and sees it hits 17.5 newtons per square millimeter. Because the strict allowable limit is 16.5, the elastic method rejects what is actually a perfectly decent beam, forcing an uneconomical redesign. Next, the ultimate method looks at the exact same beam, multiplies the load by 1.5 to get 180 kilonewton meters, and compares it to the ultimate capacity of 250. It wildly cheers passes, totally ignoring the fact that the 17.5 surface stress will absolutely cause microcracks over time. Finally, the limit state method steps in. It checks the ultimate strength and says, yes, we're good, it won't collapse. But then it checks the serviceability limit state, catches that 17.5 stress flaw, and flags it. It fails the beam, but it doesn't do it blindly. It forces us to intelligently redesign the depth to just 450 millimeters, ensuring safety against collapse and durability in daily use.
And this leads us perfectly into our final section, Part 5, Intelligent Distribution of Safety. Now, what's really fascinating about this final verdict is what it means on a macro scale. This isn't just about math on a whiteboard, it actually impacts a whole nation's resources and economy. As Professor Arvind Deshmukh brilliantly explained to a student named Vikram in the source lecture for today, we cannot just use a massive blanket factor of safety of 3.0 to guarantee a bridge won't fall down. Why not? Because society simply cannot afford 3 times the cement, 3 times the steel, and 3 times the cost for every single infrastructure project. By using a scientific, targeted factor of safety, we build just enough strength to last 100 years, without any excessive, wasteful brute force. It truly is the intelligent distribution of safety. And that brings us to the homework from the lecture, leaving us with a final thought for you to solve. To fix our beam's serviceability failure, we could reduce the eccentricity of the pre-stress, or we could increase the concrete grade to M60. Which one will you choose to optimize your next structural design? What exactly is the perfect balance of economics and safety? Let that provoke your thinking as you review these concepts. Keep practicing, and I will see you in the next explainer.